Hey guys, this is Mr. Galoya again. Hey, today we have a short video on notes, and this is from a new packet. This is notes about objects getting slower, and that concept is called negative acceleration. So, you know, we can do this. Here's kind of the notes here, and this is called Unit 3B, and you know, we can do this in a car, right? We can put the foot on the brake. So we see the speedometer of our car. We see the speedometer of our car, you know, at some value, maybe 60 miles per hour, and that speedometer gets less and less and less. The car may come to a rest, it may not, but our speedometer now shows numbers that are decreasing. That concept really is called negative acceleration. Now, we've already learned the acceleration formulas, right? We've got two of them. We've got the how fast formula, and we've got the how far formula. So let's kind of rewrite those down. You know, the how fast equation, VF equals VI plus AT. Now this is then again a linear sort of relationship that we saw with objects getting faster. So this is based on the equation y equals mx plus b. The vi then represents the initial velocity, the a represents the acceleration, the t's for time, and this would be your final velocity. Again, that's why we call it the how fast equation, because you can use this equation to determine how fast objects are moving. Well, the how far equation then is based on a quadratic. It's based on a parabola. And we can write delta x equals VI t plus 1/2 AT squared. Some textbooks write it x sub f equals 1/2 AT squared plus VI t plus x sub I. So depending on kind of the textbook that you have, you might see it this way, you might see it this way. Again, this is based on a quadratic, a parabola, and in a math course we would say y equals ax squared plus bx plus c. And all of our terms kind of match up there with what we would see with the quadratic equation in a math course. So let's say we have something like a car or an object that's slowing down. So let's say the car, in this case we're dealing with meters per second, but it could be miles per hour. Let's say the car has an initial speed of 50. That would be our VI, and that speed is dropping every second. It's dropping by 10 units. So in 5 seconds we go from 50 to 40 to 30 to 20 to 10, and then finally the car is not moving at the 5th second. So let's again start with the velocity time graph, and let me maybe change colors. So there's my VT graph right here, and here are then my points. Now again, on a VT graph, this acceleration can be seen as the slope. Now instead of having a positive diagonal, we have a negative diagonal. Okay, can you see that there? That's a negative diagonal. Okay. The slope again represents the concept acceleration, a number. In this case, we're decreasing by 10 units of velocity every second. So my slope then would be -10. That'd be my slope or my acceleration. So in this column here, we have a constant acceleration of -10. So I can fill that in on my table. That allows me then to create an acceleration time graph, and again that's going to be then a horizontal line. That's called an AT graph. Okay, so my points all stay constant at -10. All right, now what about, so we've got two of our graphs, the AT and the VT, but what about the position time graph? Well, that position time graph, we can get the points from that by using our how far equation. So we can say, okay, delta x equals VIT plus 1/2 AT squared. All right, there's my general equation, right? Can you see it there? VIT plus 1/2 AT squared. We now know the A is a minus 10. We know the VI is what the car had initially. That'd be 50. The time then can change. So we can leave the time as a variable, and I could write 50 times t plus 1/2 times a negative 10 times t squared. So let's kind of work this for t equals 1. So we could say at the end of the first second, where is my car? Well, or how you might say how far did my car go? Well, if we put in 1 second, we get 50 times 1 plus 1/2 times a negative 10 times 1 squared. So that would be 50 minus 5, or 45. Okay, so we start at the origin. Again, that's called the reference point. Okay, we start there, and by the end of 1 second, I am 45 meters further down the road. Okay, now let's do it for then t equals 2 seconds. So that's going to be 50 times 2 plus 1/2 times minus 10 times 2 squared. Okay, can you work that out? I hope you can. So that'd be 100 minus 20. Let's see, did I do that right? 4, 2, minus 20. So by the end of the second, I'm now 80 meters down the road. We can do this for t equals 3. So that'd be 50 times 3 plus 1/2 times negative 10 times 3 squared. Don't forget to square things. Okay, so that's going to be 150 minus, what is it, 45? So that would be then a total of 105. Okay, you notice then we're starting to see a curvature here, right? We can do this for t equals 4, and that you should get an answer of 120, and then t equals 5, you should get an answer then of 125. Now, at 4 seconds then, 120, so that's going to be here, and then 125. So do you kind of see what we've got here? This again is a quadratic. It is a parabola, right? But now we have a bottom opening parabola. And again, we're seeing just one lobe of a complete parabola. Okay, so that is a quadratic that's now a bottom opening parabola. Now, again, we can use tangent lines. We can talk about the concept of a tangent line. Here, let me get another color. We can talk about a tangent line being then how fast, right? So the car starts with a pretty high slope, right, a positive velocity, and that tangent line gets less inclined over time, right? So my velocity is getting smaller and smaller and smaller. Finally, then we have a horizontal tangent line, and at 5 seconds, and I've stopped. So this is negative acceleration. The velocities are positive ideas here, positive concepts that are going down, and my position then represents motion away from a reference point, positive motion, but yet how much position change, or the distance that a car goes as it's slowing down, becomes less and less over time. So see, the first second I went 45. Let me get another color here. In the first second I went 45 units. In the second, from 1 to 2, I go an additional, let's see, that was 80, so additional 35. And then 25 additional units. and then 15, and finally just 5. So how much I go in each succeeding second becomes less and less. That's what's happening when you slow your car down. Okay, you get this parabola here, but now it's opening towards the bottom. The A is negative. In terms of the quadratic, we'd say x sub f equals 1/2 times my A. Look at my equation here. That'd be negative 10 t squared plus 50t, and then plus my x sub I would be 0. And you could simplify this negative 5 t squared plus 50t, and that's going to equal to your x sub f. Well, let's go to page 2 here. You guys doing great stuff. Well, you know, before we do that, let's kind of do our table here. So we have, I just saw that we hadn't done that yet. So we're going to have 45. So at t equals 0, I'm at 0, and then 45, then 80, and then we have 105, and then 120 and 125. And we can put those distances in on a motion map. So we start at time equals 0, then we go 45, 80, 105, 120, and then 125. You see what the spacings do here? This would be a timing dot. Time equals 0, time equals 5. My spacing then decreases, right? For an object that's getting slower. We'd see that on our ticker tape too, wouldn't we? Okay? So I redo that using Logger Pro. I redo that parabola here, right? There's that parabola. And so again, this would be our position time graph. It's showing us how far the object is going. Position time graph. So we start out pretty, there's my tangents, we're starting out pretty fast, and then my inclination then slow. So velocity is positive, but it's getting smaller and smaller. Now, could we come up again with an average? Yes, we could. Do you remember how to do that? How to get an average velocity? Well, you have to take the two endpoints, right? You can take the two endpoints and you can link them together with a line, right? Okay, look, I just linked those together with this line. My two endpoints, let's see, that's 5, 105, 125. So my average velocity then would be the slope of that line. Slope of that line, that's going to be 125 divided by 5. That's going to be 25 meters per second or miles per hour. So you might say, well, where are you doing that speed? So I'm starting at 50 miles an hour. Then I'm going to 40 miles an hour. Then I'm going to 30 miles an hour, and then 20, and then finally to 10, and finally to 0, right? And so wherever this tangent line is parallel, right? So it looks like it's going to be about 2.5 seconds. These are parallel lines. So before 2.5 seconds, my tangent line has a slope that's greater than my average. I'm traveling faster than 25. After 2.5 seconds, my tangent line then shows the speed of my car that's less. Okay? This is what happens when you slow an object down, right? So when we get objects faster, we have a top opening parabola. When we slow objects down, we get a bottom opening parabola. Isn't that pretty cool? Hey, that's all the notes. I hope this all makes kind of sense. We'll talk to you later, kids. Bye.